Okay, so I have a problem here for calculating number of cycles and using all the equation of the Marin factors that we went over in class. I chose this problem because the question was incorrect according to the solutions manual, and the solution in the solutions manual was completely messed up. So I wanted you to have a practice problem with the correct solution. And so what I have here is the F diagram for that first region. So if you remember, every time we're talking about fatigue, we're gonna have that idealized SN diagram. So SF, number of cycles. This is a logarithmic scale. And so we have a gentle slope, a steeper slope, and then the plateau for the infinite life. This would be SUT. This would be F SUT. And then this would be the endurance limit. Okay, and so what I have here is the F diagram so that I can calculate this first point. And SE is going to be the result of multiplying all of the Marin coefficients. So Ka times Kb times Kc times Kd times Ke times the endurance limit for that idealized case, which is just half of the ultimate strength, as long as the ultimate strength is below 200 kilopascals or 1400 megapascals. Okay, we're going to use all of that. So let's read the problem first. I have a pin and a knuckle joint, and shown in part A of the figure, and I have these forces, these loads. Also, like, basically this is just getting pulled up, and because the pin goes through this part, there's going to be some reaction forces here and here. Okay, so if that's 600, this is going to be equal 6,000, sorry. This is going to be equal to 300 and 300. 3,000 and 3,000, sorry. I was trying to get my marker with the correct width, but it didn't work. So assume the loading on the pin is modeled as concentrated forces, as shown in part B. So what I just wrote, the shaft is made of hot rolled steel that has been machined to its final diameter. So even though it was hot rolled here, it's not working well. Hot rolled, it has been machined. So when I'm looking for that surface Marin coefficient, I'm going to look for machined, not hot rolled, because that's like those are the ones, that's the finish of the surface. And then based on the stress element on the outer surface at the cross section A, determine a suitable diameter of the pin. So I want to find D to provide at least a factor of safety of 1.5 for both infinite fatigue life and for yielding. So that's what we're going to change. So we're going to do for yielding, we're going to find a D, and then with the D I'm going to either calculate if it's never going to fail, if it's going to have an infinite fatigue life, or if it's going to fail, what are the number of cycles that is going to bring that part to failure. Okay, and we're going to add some couple of things so that we can practice everything that we went over in class. So we're gonna let's say that this operates at a temperature of 300 degrees Celsius, and that I want a reliability of 99.99%. Okay, so we can use that information for basically K, D, and K, E. Right? So first thing, I'm going to calculate this diameter based on yielding. So from this steel, I'm going to need the properties. So I look those up in table A20, and I find out that the ultimate strength is 400 megapascals, and the yield strength is 220 megapascals. So, well, this is not necessary, but just so that you have an idea, I have a yield strength here of 220, and then an ultimate strength somewhere here of 400 megapascals, right? So basically, if I didn't know that this was a fatigue problem, because the joint is subject to a repeated applied and released load of 600 newtons, so that's going to give me that fatigue. If I didn't know that, I would just basically look at the yielding here, and my factor of safety, and with that I would just calculate the diameter. But I know that because it's a cyclic loading, this is gonna undergo fatigue, and so I want to know how many cycles that's gonna be able to withstand. Okay, so let's just use this first part of the information. I have 3,000 newtons going up, 6,000 newtons going down, and the distances would be 20 up to here and 20 in millimeters. So the distance from here to here would be 10, half of 20, and 5, half of 10. Okay, so 15. And so this is super simple. I basically would do my shear and moment diagrams. I'm not gonna waste time with the units, but actually let's do it. This would just be newtons, and this would be newtons millimeters. I am gonna need that. So I'm looking at this free body diagram, and what I see is that it goes up 3,000, at the middle it goes down 6,000, and then at the end it goes up 3,000. Okay, so for the moment diagram, I would just have this slope of 3,000 times 15. So basically this value right here would be 45,000 Newton millimeters. And this is the maximum moment that it has to resist. So from this equation, well, we would do sigma my over I, but we already know that for a shaft this is going to be 32m over pi d cubed. We've done that 1,000 times in class, and I know that the factor of safety is yield strength over the stress. So if I solve for this, again, we've done this 1,000 times, we get a diameter using, well, again, we've done this 1,000 times, so I already know that it's going to be 32 times the factor of safety times my moment, okay, divided by pi, and the yield strength, which in this case is 220 megapascals. So megapascals, Newton millimeter, and to the 1/3. Okay, and that diameter gives me a value of 14.62 millimeters. Okay, so the problem says something about that. Determine a suitable diameter of the pin rounded up to the next millimeter increment. I'm going to assume that the next millimeter increment would be 15. But again, I need to find what the stress is. Okay, so this will guarantee that the factor of safety is at least 1.5. But since I'm going a little bit up, I can also calculate what my stress is going to be. So the stress, which is 32m over pi d cubed, gives me a value of 135.8 megapascals. So I'm done with the first part. I already know what the suitable diameter is for the pin, rounded up to the next millimeter increment, and that will provide a factor of safety of at least 1.5. Now I go to the fatigue. So I know that maybe the endurance limit, this value right here, is going to be lower than what my current stress is with the design that I made. Okay, so that is going to be very important. If it's lower, if sigma is lower than the endurance limit, we're fine, and the part is going to live forever. It's not going to break, no matter how many cycles I subject it to. But if sigma is greater than SE, I know right here that if sigma, have it somewhere over here, it's going to fail. Okay, and I want to know how many cycles I have. Okay, that's basically my question. So I'm going to calculate first SE to know if sigma is below it and we're safe, or above it and we need to calculate how many cycles it's going to support. So to do that, I will start with this. The first approximation is just half of SUT, like I mentioned at the beginning. This is true if my sigma, or my ultimate strength is below 200 KSI or 1400 megapascals. Okay, so since my ultimate strength is indeed below 1400 megapascals, it's only 400 megapascals, I can use this first approximation. So with this, I know that SE prime is 0.5 of 400, which is the material property, so 200 megapascals. And now I'm going to find Ka, B, C, D, and E, multiply them all by this number, 200 megapascals, to find the actual endurance limit. Okay, so just as a reminder, surface size, temperature, reliability, and loading, right? So we're going to do all of those 5, and I basically put here everything that we're going to need. Okay, so as I mentioned before, the problem said it was hot rolled, but it was machined to the final diameter. So if it's machined, I'm going to use, and I'm using megapascals, I'm going to use this A coefficient and this B coefficient to calculate the first thing that I need, which is the surface Marin coefficient, which is A SUT to the B. So this would be 3.04 times 400 to the minus 0.217, which is equal to 0.828. So I have that first one. Next one, the size. So KB is size. KB, if I have the diameter, and the diameter I know I have calculated was 15 millimeters, I would be between 7 and 51 millimeters. So I'm going to use this equation for KB. So KB is equal to 15, or just, 15 over 7.62 to the minus 0.107, which is equal to 0.93. So I already have Ka and Kb. Kc is the type of loading. So this is under bending. It's not pure bending, there would be some shear, but like I explained in class, we barely ever consider that, because most of the shafts that we deal with are longer than wider, so that shear, that transfer shear, is almost not going to contribute to anything. So bending means that Kc is equal to 1. I know I added to the problem that the temperature, the working temperature, is 300 Celsius, so I can get my KD coefficient, KD coefficient from these equations. The first one, so this equation in the book, the first one is for Fahrenheit, the second one is for Celsius. Since I have Celsius here, KD would just be equal to 0.99 plus 5.9 times 10 to the minus 4 times 300. It's already in Celsius, which is what I needed here. Okay, and then I'm going to use it on the other side too. Minus 2.1 times 10 to the minus 6 times 300 squared. Okay, I do that calculation, and then my KD is equal to 0.978. right? And finally, I also added to the problem that I wanted a 99.9% reliability. Oops. So I have a table in the book 6.4 that will give me the factor for that. So KE is equal to 0.702. I have all of these values for my Marin coefficients. So KA for surface finishing, KB for size, KC for the type of loading, KD for the temperature of operation, and KE for the reliability that I want in my system. Okay, so basically I grab all of those and I have SE, just like I showed here, and this is going to be just SE would be equal to KA, KB, KC, KD, KE times SE prime, which was the idealized one. Okay, so this is 0.828, which was this, 0.93 for KB, 1 for KC, 0.978 for the temperature, 0.702 for the reliability, and SE prime was already here as 200, which was just half of the ultimate strength, which was 400. Okay, so SE will give me a value of 106 megapascals. Now I know that the actual stress that I have due to the forces, the external loads on my system, is higher than the endurance limit, the actual endurance limit. So basically when I go back here, I'm going to have an SE equal to 106 and a stress of 135.08. Okay. So let's work with this again. I'm gonna redraw that diagram. Actually, no, we can use that. So I have a linear relationship here. Let's do it in green. I have this linear region that I know is where I'm gonna end up doing locating my points, so that I know how many cycles I can subject the pin to, and that equation is given by SF, the fatigue failure. So any point in the y axis is equal to a n to the m, where n is the number of cycles. So n is the x-axis, SF is the y-axis. I know that my SF is going to be sigma, and my n is my variable, but I still need to find a and b, so basically the slope and the shift, or the y-intercept of this linear equation in a logarithmic scale. So let's do that. I need to find this point and this point to be able to find a and b. We did this in class. So a was equal to f SUT, which would be this point here. A fraction of the SUT, which can be found using this diagram, squared over SE. And then again in class we solved for b. B would be minus 1/3 log. So this is a logarithmic scale, and it's 10 to the 1, 10 to the 2, 10 to the 3, and then 10 to the 6. So that's log base 10 of f SUT over SE. Okay. So I need f. I have SUT is the 400. So I have this. I have SE, which I just calculated, the endurance limit equals to 106, and I only need the f, which I can get from this diagram. Okay. So my x-axis is either in megapascals, or megapascals at the top, or KSI at the bottom. And what I find specifically for this problem is that my SUT, which was 400 megapascals, is not even in this region. So I'm going to explain one more thing. When the ultimate strength is below this diagram or below the equations that you get for this diagram, experimentally what you see is that this is very scattered. So like if I were to continue this plot here for values lower than 500 megapascals, the experimental results would be here, and they're very scattered. So they actually don't fit this curve, this curve that I have here. So basically that means that if I want to be very conservative, I would just grab an f of equal to 0.9, which is this value right here, right? Okay, so I have 0.9 for f. SUT is 400, SE is 106, and with that I can calculate an A of 1223 megapascals. So of course this A has to have units of megapascals, so that when multiplied by number of cycles to the B gives me megapascals, megapascals for the SF. Okay, and B, with the values I have, will give me minus 0.1770. Okay, and basically that's it. I want to solve for n. So n, I don't know what it is, but I do know that SF, the fracture strength, has to be equal to the actual stress that I'm subjecting it to for it to fail. Okay, so basically I rewrite this equation. I'm gonna just keep whatever we have this already. So I'm gonna erase this right here, and basically what I said is from this equation I'm gonna solve for n. So n would be SF over A to the 1 over B, with SF equal to my sigma. Okay, when the SF from this diagram right here is equal to the stress that I'm subjecting it to, it will fail. Okay, so 1 over B, and in numbers this would be 135.8 over A to the minus 1 over 0.1770, which is basically this value here. And then my number of cycles is equal to 247,000. Okay, so let's look at this again one more time. We usually start with a real world application, so you're probably going to get something like some kind of structure here, and some conditions. We know properties of the materials or what material we're using. So for example, I know what steel I'm using and how it's been either processed or obtained to a final diameter. So that's going to give me information about the surface and will be useful for the first Marin coefficient. I know in this case I want to calculate, I want to design it for a specific diameter, but once I find that diameter I will have information for the size, which is the second Marin coefficient. Okay, this is moving. So we have Ka, because I know it's machined to the final diameter. If I have the diameter, I can calculate the second Marin coefficient, the size coefficient. Due to the loads, the distributed loads here, I know that this is gonna generate some bending. So I know that because it's bending, Kc is gonna be equal to 1. I know that this is being operated at a temperature of 300 Celsius. I added that, but it's probably a given. You know what temperature something you are building or designing is going to operate at. So that allows you to calculate the fourth Marin coefficient, temperature coefficient. And every time you're designing, you want to know what the reliability of what you're designing is. So that can be accounted for with another Marin coefficient. Okay. Okay, so basically the first things that we did here won't change. We have some external loads in our 3D structure, even if we're looking at it as a 2D schematic. With that, we can design the ideal diameter. So we've done that 1,000 times. And with that diameter and the properties of this material, the material that we were given, we can calculate the endurance limit. The endurance limit either has to be lower or higher than the actual stresses. If the endurance limit is higher than the actual stresses, we're fine. The piece is gonna be able to withstand an infinite number of cycles, so we're good. But if the stress is higher than the endurance limit, we know that at some point it's gonna fail, because the stress would be higher than the fatigue strength. The stress would be higher at some point than the fatigue strength given by this curve. And so basically what I could find in that situation is the number of cycles. Okay, so all of these problems are almost reduced to finding the endurance limit. The endurance limit, the ideal one, is just half of the ultimate strength, but we use the Marin coefficients to get like the actual or a more accurate and more conservative real endurance limit. Okay, and then because we know this is a straight line, we use this equation to either solve for the number of cycles, or if I know that this structure or part is gonna be in loading and unloading for a specific number of cycles, I could also solve for the fatigue strength and calculate in that case something like the fatigue factor of safety. So just to finish, I'm gonna explain this. Let's say I know that this part is gonna be subjected to 10 to the 5 cycles. Okay, so 10 to the 5 is way lower than the cycles needed for it to fail. So basically I could just send 10 to the 5, go up here, find my F, my fatigue strength. So let's say this is, I don't know, 150, and my stress is only 135. I could calculate this fatigue factor of safety as 150 over 135.